Okay, so simply put, it's just whether it's opening upward or opening downward. So concavity is basically this right here. So concave up, decreasing, concave up, increasing, etc. So very, very simple. Here's an official definition. So basically, it's concave up if all the tangents on the curve are below the graph, so they're kind of going downward, right? Below the graph. So the beginning of the homework, where'd it go? We're going to use the second derivative to determine whether it's increasing or decreasing. So the first derivative from last time on Tuesday, we talked about the first derivative test on 4.3, which told us about increasing and decreasing. We were able to kind of figure out if there was a maximum or a minimum there. Let me pick a simple question first. Okay. So the question will just be determine the intervals when f of x is concave up or concave down. Okay. Step one, find the critical points. And y'all remember, right? We just take derivatives, set equal to zero. So here we go. What is the first derivative? At this point, I'm hoping y'all are, you know, pros at these types of power rules. What do y'all think? This is F.
2x minus 2.
I believe in y'all though. So once you have this, set equal to zero. So for x, and y'all agree that this is 4, right? Oops, made a mistake, didn't I?
Were you asking if x squared minus 2x plus 8 was the derivative? Oh, okay. I see you're fixing
Yeah,
it.
I was asking what the derivative was. I think I heard y'all wrong. I'm gonna blame myself. There we go. So x will be 1. So we have a critical number. Oops. Okay. Step two. Find the second derivative. What's f double prime?
Just two.
Yeah, just two, right? Okay, so this is just a big reminder, right? The original function, you plug in points and you find locations on the graph, right? Just points on the graph. You take a derivative, and if you plug in numbers, you find the rate of change at any given point on that graph, which is related to the slopes of tangent lines to each point that you choose. That's what derivative does. Second derivative can tell you about concavity. So whether it's, opening up or down, increasing, decreasing, that kind of stuff is related to this, concave up or concave down. Some books might use the word convex or and concave, but who cares? I don't really care what you call it. Now, although if you plug in a number to the first derivative and it's positive, then it is increasing at that point. If you plug in a number here and it's positive, then it's concave up at that point. But what do you see? What do you notice about this second derivative?
It's positive.
It's always positive, right? For any x.
So that means it's upward.
Pretty much it is always upward, which makes sense. What kind of graph is this? We should already know, right?
Are you asking what graph? The parabola?
Yeah, it's a parabola. It's always opening up. So basically what we just proved is that it's always opening up for any x. The parabola is always concave up. So we kind of already knew that, right? But now we showed it with calculus. So let's put that into one second. Since the second derivative is always greater than 0, for any any x, then it is always concave up. Okay. So we can see it fits that what was that picture? There it is. Fits these two shapes, right? concave up everywhere. So the interval, so f of x is concave up on this interval. So this question wasn't all that interesting, but I think it's a nice, easy problem. So, kind of get started. Is there any questions on what concave means? All right. You guys cool on example one then.
Yeah, so that means that it doesn't have a downward, right?
Yeah, it's just always opening upwards about it.
Okay.
So let's choose a cubic function.
And the
That,
homework says DNE, like just put DNE,
oh, does it? Let me see.
or does not exist. So that's what I was asking.
Oh, you mean for the downward, right?
Yeah.
Yeah,
Yeah.
I would DNE for that one. Let me see. Yeah, that's it. Let's do number 3. Any other questions on number 1 type of problem? Okay, cool. Let's move on then. So let me know. Determine the intervals for concave up and concave down. With this function, negative x cubed plus 3x squared. I wrote that all weird. Plus 7x minus 1. All right. And I'm going to go ahead and, no, that's all. That's all. It's fine. Start slow. Step 1. Find f double prime. Last time we did the inflection points and I didn't use it because we're not doing max or mins just yet. So we'll wait on that. Let's just answer the question. That's it. What is the first derivative? Yeah, negative x squared
Plus 6x
plus
plus 7.
6x, yeah, plus 7. Excuse me. So second derivative. Should be simply what?
Negative 6x plus 6.
Yeah, right? Just do your power rules. That's it. Okay. Step 2, find your inflection points. You guys know what an inflection point is? Right. Basically, if you have a change in concavity at a specific point, that is considered to be inflection point. And that happens when the second derivative is equal to 0. So it's like a special critical point. Well, I was hoping I watched the videos, Chance. That's all right. So here we go. Set this equal to 0. Okay. So this point is an inflection point. I want to show you on the graph exactly what it looks like so you won't forget. So I feel like everybody's more visual, right? Excuse me. All right. Make sure I wrote all this correctly. Yeah, right there. You guys see the graph?
Yeah.
So you see before at 1, right? It's concave up. It's opening upward. And then right after this point, the inflection point, we're now opening downward. So going from one concavity to a different one, that's your inflection point. It's hard to see it visually, right? So we gotta find it first, and then we can talk about, you know, where are we concave up and where are we concave down. Does that make sense? That where we're going with this?
Yeah, that makes sense.
So given once you have that, you can give the intervals. You can answer the question. So let's go ahead and do it. But let's say we didn't have the graph, right? You would have to use the test to figure out where we concave, up or down. And since we know it changes at 1, here we go. We'd have to test around it. So just like the first derivative test, you guys remember from last time? Plug in a point before, plug in a point after, See what we get. So -6 times 0. You agree that this is positive, right? Plug in 2. Negative. So we were concave up here, concave down there, which we saw on the graph, right? So answer the question, what is the interval to be concave up?
-infinity 1, comma 1.
Yeah. Concave down. Would be here, right?
Yeah, 1 to infinity.
So basically, if I don't think I wrote the note here. If f double prime is greater than 0, then concave up. Got a happy face. Concave up. If f double prime is less than 0, then concave down. Sad face. Hopefully that helps you remember. Maybe not. I don't know. But that's what we did right here. The 6 was positive, so I knew it was opening up. The 2 gave me a -6, so I knew I was opening down afterward. There was only one point of inflection, so it was opening up all the whole time until this point, then opening down afterward, because there was no second change in concavity. It was the same. Does that make sense?
That makes sense.
Any questions on example 2? So they just want these intervals. And you test around the inflection point.
So it's almost like the last part we did 4.3. You're just adding that upward and downward thing.
Yeah, pretty much, right? This is very similar to the first derivative test. It's just that the first derivative tells you something else, second tells you another thing. So they can actually both tell you about maximums and minimums. Well, let's do that next. We're going to find a minimum using the second derivative. So this technique we're about to do is a little easier than because you don't have to test around. Because if I have a critical number and I plug it in, right, it's going to be opening up or down depending on the sign. So I can just say, well, it's a maximum or minimum depending how it opens. All right. So I'm gonna move on. You guys cool on number 2?
Yeah.
Okay. So let me know. Find all relative. extrema of the function using the second derivative test. So we're still going to need the critical numbers. Here's the function they want us to work on. I forget what this was on the homework. Okay. This time for real, step one, find the critical numbers. We will use them. So what is the first derivative? Yeah, 4x cubed minus 12x squared. Okay, so this will be easy to factor, right? It's just two terms. So factor this guy. So first set equal to 0. They both have 4x squared in common. With brackets for no reason. I don't know why I did that, but same thing. Set each part to 0. All right, so we have two critical numbers. Step 2. Find f double prime. What's the second derivative? The second derivative will be, let's see, 12x squared minus 24, right? That's okay. Participation means a lot to me, so it matters to me. All right. So now once you have this, set it equal to 0. Solve for your x's, and then you'll have one or maybe more inflection points. We'll see. Looks like 2. Find the inflection points. Well, actually, hold on a sec. Yeah, I don't need the inflection points because all they asked for was what? extremum, max or minimum. Although, let me think here. You could have a critical number that also becomes an inflection point. And if that's the case, we should probably rule it out as a minimum or maximum. Mm, no, actually, it doesn't matter. Yeah. Yeah, never mind, because it doesn't matter. That's not right. Just, I don't want to do more work for no reason. Step three is just plug in the critical numbers. Into F double prime. So here we go. F double prime at 0 is 4 times 0 minus 13, oops, 12 times 0, which is 0. Double prime at 3. We have 4 times 3 cubed minus 12 times 3 squared. That's definitely positive. It's 36, right? This tells us positive, so concave up. So if it's concave up, does that mean minimum or maximum? At 3. Yeah, minimum, right? I think it was.
We're supposed to be using the second derivative, right? I think you're using the first.
Oh yeah. Dang it. Second derivative. Yeah. Okay. Let me fix this. Thank you for not working that out. All right. So it'd be 12 times 0 squared minus 24 times 0 equal to 0. That is neither positive nor negative. So uh, inflection point. So now we're going to do 3. I think this is 36 from my notes earlier. Let me double check myself this time. Yeah. Okay. So let's graph it and see if it's legit. There's the inflection point. Here is our max and, or sorry, a minimum. Anyway, so since I knew it was concave up here, we didn't have to do the first derivative test. That's another function of the second derivative. So I recommend if you're trying to find a max or min, find the critical numbers and just plug it into the second derivative. That saves you work. The only time you don't want to do that is if finding the second derivative is just a real pain. Then, like, let's say finding the first one was just like chain rules and product rules and all this nonsense. Then you probably don't want to do a second one on that same function. At that point, just do first derivative test. But if it's some simple one like this, right? It's a basic power rule, then you might as well just take a second one and use it to your advantage. Assuming the question says find a max or a min, right? Local max or local extrema. Same thing. Guys have any questions on example 3? Oh, yeah, you gotta plug that into the function. Basically, this right here is f of 3, so you gotta plug it in. Okay, so that's the end of 4.4. Do you guys have any questions on concavity? Do you see how the second derivative test works? Any questions on inflection points or max and mins? Let me check the schedule, see where we are at. This is the week of 320. I see. Hmm. All right. Well, I'm trying to see if we're ahead or not. Might have to do one more section. Because we already did L'Hopital's rule a long time ago. You guys remember? It was like, I want to say around test 1 time. Does that ring a bell? So if you're taking a limit, if you have an indeterminate horn, then you can use L'Hopital's. To find the limit.
No, I think we did cover some of it, and then also the book talked about it a little bit, but we never did the homework.
Okay, yeah, that's fine. I'm sure we. I don't remember what we said anymore, but it's all good. Oh, by the way, indeterminate. Means 0 over 0 or infinity over infinity. So if you have those scenarios pop up, we'll then do L'Hopital's. So you should see right away when you factor, this top part becomes what? X minus 10, x plus 7, or x minus 10. So when I take the limit, you'll see it's going to be 0 over 0. Since I have an indeterminate form, indeterminate form, then we can use L'Hopital. So here we go. And all L'Hopital is you do a derivative of the top and bottom without doing any quotient rule. You do them separately. So I'm using my L'Hopital rule right here. So you get 2x minus 3 over 1. Right? What is the derivative of the top? 2x minus 3. Derivative of this guy is just a 1. So now take your limit, and what do we get? Yeah, it looks like 17, yeah. So you see, at first we couldn't do it. Do L'Hopital, and then we can. We no longer have an indeterminate form. So the limit will be 17. Any questions about L'Hopital's rule?
It's pretty simple.
So
Yes.
it's just the derivative over 1.
Yeah, you do dirt to the top and dirt to the bottom, but you do them separate.
Oh,
You see dirt to the bottom is a 1?
yes, I see it now. Thank you.
Okay.
So that's only if it's, oh, indeterminate. Yeah. Okay, never mind.
Yeah, you have to have the indeterminate form. So it makes the limits really easy, but only if you have 0 over 0 or infinity over infinity, then you can do this. Okay. Let's see here. Does there anyone have any questions on that idea? You want to do it one more? Does that make sense or no? The only change on the other questions, let me show you. Um, it, when you plug in 0 here, it's going to become 0 over 0. So you can do the exact same thing we just did. The only difference now is the derivative of this top part is a chain rule, so it's kind of shitty. It's not too bad. Same thing here, chain rule. So like the difficulty of these questions only change depending on the how hard the derivative is, not the L'Hopital part. L'Hopital is pretty basic, right? Just check is it indeterminate? If so, do the derivative top and the bottom, and then try plugging it in. If you plug it in and it ends up being still indeterminate, then take another derivative of the top and bottom and try plugging it in again. That's all you got to do. It's pretty straightforward, I think. Okay. Now we'll stop